Okay, so am I audible to all of you?
Yes, sir. Screen is visible and you're audible, sir.
Okay.
Yes, sir.
So we'll continue. We will continue our discussion with imperfections in solid. So this was the slide we are discussing in the last class. So this is the equation. This is an equation probably you are familiar with. This has been written in a slightly different form, but you know this equation. This equation is known as Arrhenius equation. Now, Arrhenius equation is applicable in some of the processes known as thermally activated processes. That means the rate of the process. Now, this left hand side, let us take this left hand side NV divided by capital N. This as rate of the process equals to, here will be some constant. This constant has not been given anyway. This rate of the process is proportional to this quantity, E to the power, minus this. So this is the equation. So if you put this one constant here, it is better. And that equation is known as Arrhenius equation. So rate is actually dependent on the temperature. Rate is dependent on temperature. And how is the dependence? We will try to understand. Now let me give some example. Let me give some example of thermally activated process. In the, you see, in the next, our next topic of discussion will be diffusion in solids, and you will find that diffusion in solid is a thermally activated process, and this is a very important process which is used to different types of used in different types of practical applications. We will discuss there when we will be discussing the diffusion in solid states or solid state diffusion, and that is a thermally activated process. Then another term we have already used, creep rate. Creep, it actually depends on temperature. Then you can say the electrical conductivity. Electrical conductivity of a material also depends. We will see how it depends on temperature when we'll be discussing about the semiconductor devices and electrical properties and all that. So there are so many there are so many processes which are known as thermally activated process, and also this production of point defects. Production of point defects is also a thermally activated process. Now, what does this equation involve? This equation involves different notations, like NV indicates the number of defects that will be produced at an absolute temperature capital T, and capital N denominator capital N indicates the total number of lattice sites. See, in this example, if we consider this as the total number of lattice sites, then the probability, this actually gives the probability that uh, uh, a defect will be generated. That probability is given by this expression. So the probability that a defect will be generated at absolute temperature T is given by this equation. That way also it can be explained. So right hand side is exponential of minus QV divided by K into T. Now, apart from T, we have K, which is familiar to us, which is known as Boltzmann constant, and it has got this value. And QV, another important parameter known as activation energy. Now, here QV will be activation energy per atom. That means if you want to, or per defect, if you want to generate one defect, then the amount of extra energy that will be required is known as activation energy. So in this equation, some of the important parameters, very important is this activation energy, and we will see how we can measure how we can measure the activation energy for a particular thermally activated process. So this is a very, very important parameter for this type of process, like production of point defects in a bulk material. So this is the explanation of this equation and their different notations. So let us see the next slide. Now, as I have told you that QV or activation energy is very important. So how to measure the activation energy is very important. So if you try to analyze this equation graphically, so you will find like this. If we take y-axis as the defect concentration in percentage of defects, how this is changing with increase in temperature, you will find that it is increasing exponentially like this. Now, if you want to measure this QV, it is quite simple. We will have to perform some experiment on that particular process, and we will try to plot this equation. So basically left hand side will be the rate, or we can say the logarithm of natural logarithm of rate, and on the right hand side or the horizontal axis it will be 1 by t. So if you transform this equation into a linear form, it will be this linear equation or linear form. Then it will have a negative slope. And what is that? If you have some values, some experimental values of rate and temperature, suppose you have got a few points, say 5 experiments you have conducted at different temperatures, and you have measured the rate for that particular process, and you plot, then you will get a plot here, 5 points, and if you feed those points in a straight line, and there is a method called curve fitting by linear regression, then you can find out what is the value of the slope, and this slope will be equal to slope will be minus qv by k. Slope will be minus qv by k. So if you equate this slope, with this minus qv divided by k, and k is known to you, so from here you can easily calculate what is the activation energy for that particular process. That is how you can measure the activation energy experimentally. Actually, activation energy can be experimentally measured. So this is very important point. So let us here take, just I have given one small problem here. So find the number of vacancies in 1 meter cube of copper. Find the number of vacancies in 1 meter cube of copper at 1000 degrees centigrade from the following data. So all data has been given here: density, then activation energy, 0.9 electron volt per atom, atomic number, then you have got the Avogadro number, whatever you want for calculating, you can find out. You can find out from here. So this problem you try to find out the answer. What will be the value? What I want you to find out is that you find out the value of NV. They put these values there, so you can easily find out what will be the number of vacancies. So this this is already given, so solution is also given. Next we are coming to the one-dimensional defects, which is known as line defects. In other words, these one-dimensional defects are called the dislocations. So dislocations are the line defects, and these are slip between crystal planes actually results when dislocations move. So dislocation lines, when dislocation line moves, then slip occurs between the crystal planes, and it produces permanent deformation. So initially when I was telling you how come the plastic deformation takes place, I just mentioned the name dislocation. So dislocation is basically the permanent deformation and when the dislocation line moves. We will see in subsequent pictures, diagrams, and we will try to understand how dislocation line moves. So when the dislocation line moves, what happens? Permanent deformation takes place and you get permanent deformation takes place because of the movement of dislocation lines. Let us see how it happens. So just one schematic diagram here. Now this is a diagram which shows that before deformation, before application of any load. But when you are applying some tensile load or tensile stress, there will be some slip line. Now this slip line actually is because of movement of dislocation lines. Now here it will be not easier to understand how come this dislocation line moves. So we will have to go into the deep of atomic structure. So we will try to visualize it with the help of atomic structure in the subsequent diagrams. So let us just see what are the different types of linear defects or dislocations. These are these are one-dimensional defects around which atoms are misaligned, and it has got two different types. One is called the edge dislocation and another one is called the skew dislocation. So there is a difference, so two different types of dislocations, and we'll try to understand. And one of the very, very important parameter in this dislocation motion or in this type of defects is the Barger vector. Barger vector, you will try to remember this name, Barger vector, which is denoted by B. Now in case of the edge dislocation, what happens? There will be extra half plane of atoms inserted in a crystal. We will see it in the diagram. So there will be extra half plane of atoms inserted in a crystal structure, and Barger vector is perpendicular. Barger vector is perpendicular to dislocation line. So these are the two criteria based on which we can say that the dislocation is the edge dislocation. On the other hand, for skew dislocation, you will see the spiral planar ramp resulting from shear deformation. We will see it. Unless you see the diagram, it will not be clear. And Barger vector will be parallel to dislocation line. So this Barger vector is a measure of lattice dislocation, and also there is a relationship with this Barger vector and the stress applied. So this linear defects of dislocation will actually take place because of application of shear stress. So there is a formula. I am not going into the detail because we have certain limitations, time limitations, but there is a relation between the applied shear stress and this Barger vector, and that will tell you how much stress will be required to perform this plastic deformation, and all these calculations can be performed once you know the Barger vector, and it can be quantified. Next, so this is the slide. Try to understand the edge dislocation. Now, this is the atomic arrangement in 3 dimensions. So obviously, when you are looking from this side, so this is the plane, and we have tried to draw a 3-dimensional structure, so it is clear. So you see, it is not a perfect crystal structure. It is not a perfect crystal structure because this is the extra half plane which has somehow been here inserted. How it has inserted, we will try to understand. So when this type of defect is there, we call it is edge dislocation, because extra half plane, as per the criteria, we know when there is a extra half plane inserted, then it is edge dislocation. And another thing, you see the Barger vector, which has been denoted by B here. This Barger vector direction has been given. How to determine this Barger vector, that also we'll see. So for the time being, just see here, Barger vector, this one, how come this has become the Barger vector, we will see. So Barger vector, and you see this line, the line or the dislocation line is this one, dislocation line. Actually, dislocation line here also it is not clear. This here is your dislocation line, perpendicular line. You have got a, if you look, perpendicular to the space, there is a line, and this line, the atoms which are there, which are lying in this line, which is perpendicular to this plane, is actually the dislocation line. So dislocation line is perpendicular to this page, and of course you can see the Barger vector. So Barger vector and dislocation line are perpendicular. This is another criteria. So is it clear from this diagram? Is it clear? Can you hear me?
Yes, sir. Yes, sir.
Okay, you try to understand and think a bit. So there is a dislocation line and Barger vector, both are perpendicular, and we have got extra half line inserted here. So just this diagram.
Sir, how the extra half line is inserted there?
That is what we are coming. Just see, just
Okay, sir. Okay, sir.
some of the next slides, just it will be clear, I think. Now we are trying to find out Barger vector. Just see how to find out the Barger vector. Same diagram, we have only drawn it into two-dimensional diagram. Just try to see. We are looking in this direction. We are viewing direction from this side or this side, any direction you can look. So what happens is that how to get that Barger vector. You see, now where there is a extra half plane, let us say somewhere there is extra half plane, and we see that there is a defect in that, as dislocation is there. So we will try to form a closed loop here. We will try to form a closed loop. Just see here, it is written including that particular dislocation line. So this is the point. Just see the arrow, tip of the arrow here, cursor. This is the start point, and we will try to form a loop. This is the starting point. We will try to form a loop. So what we are doing, we are, let us say we are forming a closed clockwise loop. So what we are doing, we are going towards right. We are going towards right up to this point. So actually we have moved here from a starting point till this point. So we are actually crossing 4 atoms. 1, 2, 3, 4. 4 atoms. So here in horizontal direction, we have gone to the right side up to 4 atoms. Similarly, we will just come down. We will just come down up to 4 atoms. We will come down to the 4 atoms. So when we are coming down from this point, we are coming down like this, and we have reached here. So we want to form the loop. So we will have to go to the left side up to 4 atoms. So we are going up to left side up to 4 atoms. So we are at this point, and then we are going up to 4 atoms towards the upper side to form the loop. So here from this point we are going towards the upper side up to this point. Now look at this particular point, that starting point and the ending points are not actually coinciding. If the crystal is perfect, if there is no defect, then if you form this type of loop, obviously the starting point and end point will coincide, and the value of the Barger vector will be equals to 0. But since there is this extra half plane and there is a defect, so when you are forming the loop, you will find that the starting point and ending points are not coinciding, and the vector you will have to take to close that particular loop is known as Barger vector. Is it clear?
Yes, sir.
Yes, sir. Yes.
Okay, so this is the way you can find out the magnitude. So basically here we can find out that this is the, if we can find out somehow, of course there are ways to find out what will be the values of Buddhadeb vector. So it will give you some idea regarding the stress that is to be required to apply or to deform the material. And if we can find out the number of, let us say, edge dislocation defects, so that way there are some more calculations are there that can be done. So this is some the basic idea that I am trying to explain to you. So this is the idea of Barger vector. So here also we have same diagram, we have drawn it here. So this is how you can find out the Barger vector. Let us see the next slide. Now see here, this is a very important concept, how this uh, you know edge dislocation moves and how plastic deformation takes place. So this is this is called as the caterpillar or rug moving analogy. Caterpillar moving analogy. So you see there is a diagram of different diagrams of caterpillars, and just below that it has been shown how this extra half plane moves slowly from one end to another end, and finally you are getting a final permanent deformation. So if you look at this diagram, you see, suppose you have given uh, shear stress on the top of a solid, and suppose there is a extra half plane. So chance is that the slip plane, actually slip plane will occur just below this extra half plane. So this is the red line indicates your slip plane. So the atoms will move along this or the deformation will take place along this plane. So suppose we have applied the shear stress on the top, so what will happen, this extra half plane, which is denoted by this A at this particular diagram, in diagram A, it has been shown at this position. When you have applied some shear stress, what will happen? It will move from this position to position B here. It has been shown here. So now there is a 1 unit displacement of this extra half plane. Now further application or the more magnitude of shear stress will further move it towards right side, like position C, D, like that, and ultimately what will happen? It will, extra half plane will be, come out from this whole structure. Come out means it will be on the right hand side, and there will be, this is the unit step slip, or it will be your permanent slip, permanent deformation. So that is how when you are applying shear stress, the atoms move like this, and if there is a extra half plane like that, the shear stress, application of shear stress, a magnitude of shear stress that will be required to deform the material will be comparatively less. That is why you see, when there are some inherent defects in the material, you'll have to apply comparatively less magnitude of stress. But if it is a perfect crystal, then what will happen is that you will require more stress. That is why we normally avoid, or we see while designing a component, that the inherent or residual shear stress should not be there within the materials. That is why we perform the processes like different types of heat treatment processes, like annealing, normalizing, and all that, to remove these residual stresses. So this is the idea. Now how it is related to caterpillar movement. So you see, in this first diagram, the caterpillar actually moves by moving its body, sequentially. So first it lifts its body towards the this side. Then so this is the position it will just, this position has got, that means the position of this extra half plane. Now slowly this position will actually move towards right side. So first it lifts the tail of it and try to move it slightly, and slowly this hump actually moves towards the right side, and finally the whole body gets shifted towards the light side, just like the movement of this extra half plane. So which has been shown this in green or blue color. So finally, if you see these 4 diagrams, and on the right hand side you will find that there is a complete slip along this particular slip line. So that is the idea how, from atomic structure point of view, how the plastic deformation takes place, and the concept of edge dislocation. So motion of edge dislocation. So dislocation motion requires the successive bumping or slip of a half plane in atoms. Bonds across these slipping planes are broken and remade in succession. So if you just think of the process, how it happens, how the movement happens, you can understand this point. The permanent deformation of most crystalline materials is by dislocation motion, whether you call it, so that also give you some idea about the different mechanical properties, hardness and other yield strength, everything. So most contain some dislocations that were introduced during solidification, plastic deformation, and repeat cooling. So which actually are the reasons for this dislocation motion. To deform plastically means to slide atomic planes past each other. So this is the idea. So here is another diagram, same diagram it has been given. So I have already explained. So this is given in your reference books also. Just try to see that diagram, and some explanations may be there. You can just see. So next comes the skew dislocation. Skew dislocation slightly difficult to understand or harder to visualize than edge dislocation. So if you can see this picture, if you see this picture, this see. So what we have done is that we have applied a shear stress somewhere here at this particular end, horizontally. So a part of this solid material has just shifted towards right side. You see from the diagram is clear. So some point, just let us see. Open circles, then after this diagram you have to look at this diagram, then it will be clear. Then it will look like a skew, because this is the 3-dimensional view we are taking, and here we have taken the top view. Here we have taken the top view of the diagram. So if you look from the top, it will look like a skew. It will look like a skew. The movement of the atom which has taken place within this region, actually it will, if you can visualize, it will form a skew. How it will form a skew, we'll try to understand. It has been written like that: open circles, upper half atoms. So the upper half atoms of this view, or of this top view, we are considering as the upper half, and solid circle denotes the lower half. So solid circles, although it has been drawn very small dots, so it indicates the lower half. So these two circles actually forms a screw. So the screw, if you start from here, it will be like this, it will come somewhere here, again it will go like this, and it will form a screw, something like this. And starting from here, you will go up to this point B. So it will form a screw. So screw dislocations is a ramped step in crystal planes. Barger vector, which defines the direction of the atomic displacement of the screw dislocation, is parallel to the line of dislocation. So that is why, but actually the movement is taking place along this direction. So the Barger vector is also parallel to this. So it has been shown the dislocation line by taking the right hand screw. So it is a vector which is being denoted by right hand screw notation. So the direction of Barger vector and the dislocation line, which is AB. Dislocation line is here AB. So AB is parallel to your Barger vector. So this is the screw dislocation. Slightly difficult to visualize, but to try to understand, or you can see some more books also. We have added another diagram here to show you slightly clearly. So this is the region where these dislocations are taking place. That means in the three-dimensional diagram, it is this region, between this region, this dislocation is taking place, and this is the top view of the diagram. Okay, it has been taken from Callister, so you can see that book and get further explanation on that. So this is another view, actual atomic view, front view, then top view of this screw dislocation. Now, there can be possibilities that both edge and screw dislocations may occur. So that will be a complicated one, and there will be not a simple line, but is the region, dislocation regions will be having some curvature like this. So this is the region where the deformation is has taken place, where both your screw dislocation as well as edge dislocation is there. It is slightly difficult to visualize. So screw dislocation is taking place like this. You can see. So sometimes it may happen that there can be mixed dislocations also. It is slightly difficult to visualize because it is mixed. So edge dislocations and screw dislocations both. So here it has been shown here in this three-dimensional diagram. So there is a extra half plane here, and also you have got this screw dislocation. So both are mixed here. So the deformation is taking like this. So here edge and screw dislocation, some more diagrams I have added here. So these are some more diagrams. Then the plastic deformation which takes place, that we have already discussed this diagram. Now, point is that it is there are some devices like scanning electron microscope and microscope with higher magnification. If the material materials are actually analyzed, the diagrams are taken, then dislocations can be actually visible. So dislocations are visible in electron micrographs. Here some other diagrams have been given. So this, you can see this region where this deformation has taken place. So this is the region of dislocations where the slip planes actually has occurred and atoms have moved. So in the high magnification microscopes, you can actually see the defects, line defects. Okay. So then comes the 2D planar defects in solids. So there are different types of 2D defects, like here one is called the stacking faults, and so stacking faults you will see, and another one is called the twin boundary plane. So although it is two-dimensional, although this is, you see, just plane, so along this twin plane, defects has taken place, and on left hand side or right side you have got the perfect crystal. So this will be a 2D planar defect, because if you see the three-dimensional or the perpendicular, if you imagine the perpendicular surface, which is perpendicular to this page, then this will be the plane, and this defects is situated in that particular plane. So that is why it is called 2D planar defect. So it is called twin boundary because it is the boundary of two perfect crystals. It is within the boundary of two perfect crystals. Then there can be stacking fault also. A stacking fault means if in a particular type of crystal structure, let us say FCC metals, the perfect will be, let us say, ABC. Okay, here it can be ABC, ABC, ABC like that. This is the perfect sequence. But there can be something like this. Let us say ABC, then AB, and then ABC. So you see here C is missing. So C is missing. So atoms are actually arranged by stacking in a particular plane. In a particular plane. So if a particular plane is not present, then there will be a fault there, and a different type of structure may occur there. So if this stacking fault is there, then we say this is two-dimensional defects. Let us see another diagram. The twin boundaries we have already. So you can just go through this. I'm not going into this. Twin boundaries diagrams are given. So this is stacking fault. So normally it should be ABC, ABC, ABC. This is perfect one. But sometimes what happens, the stacking, as I have already told you, it can be this perfect, say ABC, then ABC and ABC. This is the perfect FCC crystal structure, let us say. But the stacking fault may change the sequence to ABC, then AB, again AB. So at this point C is missing two times, and then again ABC. So in the region where stacking fault occurs is AB and AB. So this is a thin region, and maybe it will form a HCP type of structure, HCP crystal structure. So from FCC, so it is becoming HCP structure. So this type of problem may occur, or defects may occur. So this is called the stacking fault, 2D defect. So here is a line diagram of stacking fault. So this is the perfect one, ABC, ABC like that. One plane, atoms in one plane are arranged, one after another. So let us say three different planes are there, which makes the one unit. So it is repeated. When it is repeated perfectly, then there is no fault. But when there are the missing planes, then definitely the stacking fault occurs. Then comes the tilt and twin grain boundaries. There can be a large number of extra half planes present. So these red lines are actually extra half planes of different, length. So this length actually indicates the extra length of extra half planes. So there can be a concentration of extra half planes in a particular bulk material, so which results in tilt boundary. So tilt boundary, it will be clear if you see the next diagram. So here you see tilt boundaries. So you see here is one extra half plane, then of shorter length. Then you have got, let us say, another one of this length, then another one of this length. So basically what happens, there is a tilting of the perfect atoms which are present in a line. So this actually makes the
Sir, will these defects always happen in geometrical manners?
yes.
বলছে এই যে ধরুন ডিফ্লেকশন গুলো হচ্ছে এগুলো কি সবসময় জিওমেট্রিক্যাল ম্যানারই হবে, মানে এরকম থিটা অ্যাঙ্গেল করে একটা
these are all some basic ideas. Okay. So theoretically I can explain, but there can be, unless you understand the simple things, the complex things cannot be understood. So these are some of the basic geometries which are to be understood. Then there can be combinations also. So if there are, say, tilt boundaries and other dislocations mixed, obviously there cannot be only this tilt boundary or this type of defects, but there can be also somewhere this type of defect. There can be complicated defects also. So these are some classifications of the defects. These are some basic ideas. Okay. So there can be definitely the mixture. So only this tilt boundary, if we think that only tilt boundary will be there in some material, it is not like that. There can be some mixture. So these are some of the basic ideas. What are the different types of defects can be there, 2D defects. So this is the measure. This is the measure of tilt boundary. We have this measure d as the b divided by theta. Theta we take in appropriate this unit. So this is a measure, to have to get an idea of tilt boundary, how to find out. So these are the above three types of 2D defects. Then comes the 3D defects or volume defects or bulk defects. So these are some of the defects, pores, cracks, foreign inclusions. So these are actually some of the defects. As I was telling that we sometimes require these type of defects. Intentionally we, mix some materials to do foreign inclusions in the materials, and definitely it affects the electrical, mechanical and other properties of the material. But sometimes like cracks, suppose there is a crack inside or on the surface, definitely it will affect the mechanical properties, as we have seen in case of fatigue. If there is a small crack on the surface, let us say at this particular point, there is a small crack, and you are using that material in a situation where you have got varying load applied, definitely this may result in catastrophic failure of the material. So these are some of the points. Next important point is the stress and dislocation motion. So as till now what we have understood that if we apply stress in a material beyond your yield point, plastic deformation is going to happen. So what is that stress? What is the stress that we can apply so that there will be dislocation motion that can be calculated? So the crystal slip due to a resolved shear stress, we denote by this tower, resolved shear stress. And if you just see this diagram, so you have done this diagram, which is quite simple. Suppose you have applied in this direction a load F, cross-sectional area is A. So slip, as we have seen that in most of the ductile material, you find that there will be some slip plane in a particular direction. So in this diagram, we see that let us assume that the slip is taking place in this direction. So along the slip, we will have the applied or the stress, resolved shear stress, and there will be a normal direction. So let us see the area along which the slip is taking place, that is AS. So from here, if we just perform some calculations, on this, so this is AF in this direction, FS, let us take this angle is lambda, and another angle we are denoting, that is 5. So 5 plus lambda equals to 90 degree. So, performing this, sort of just see the notations. Tower will be Fs divided by As, and if you transform this relationship, and finally you will get a relation of resolved shear stress, which involves applied normal stress sigma into cos lambda into cos phi. So this is the expression of the resolved shear stress. Now, if we want to find out what is the critical resolved shear stress, that means the value of the resolved shear stress for which the dislocation motion will start. So definitely the condition of dislocation motion will be that the applied shear stress tau r will be greater than the critical resolved shear stress. Now for some of the materials there are certain values, critical values. Now if the applied stress is more than that, definitely the dislocation motion or plastic deformation will take place. So this is the expression, and here we have got some three different cases. So these are the same. Actually, these things have been probably discussed in your strength of material classes, into which directions your if you apply the shear stress, the deformation of the materials will be, chance of deformation of the materials will be higher. But here we have tried to understand with the help of some concept like dislocation motion. So that is what. So you must have shown there is a, if this slip plane is at 45-degree angle with the, like here you see, if your 45-degree angle, that means here your lambda 45 and pi 45 degree. So normally for most of the ductile materials what happens, this is the value, this is the plane along which the deformation normally takes place, or plastic deformation or slip normally takes place. So this is the value of tau r, which is sigma by 2. So dislocation motion in polycrystals. So here are some points noted. Slip planes and directions change from one crystal to another. Tau r will vary from one crystal to another.
Sir?
Yes.
I said dislocation motion are generally two types, conservative and non-conservative. তাহলে এই মানেটা কি স্যার non-conservative
না কোনটা?
conservative আর non-conservative dislocationের ব্যাপারটা বুঝতে পারলাম না।
Conservative and non-conservative.
হ্যাঁ স্যার।
কোথায় এটা লিখেছি?
এখানে নেই স্যার।
ও এখানে নেই।
বইয়ে দেখলাম স্যার ওটা বুঝতে পারলাম।
Conservative and non-conservative.
হ্যাঁ।
Let me think about that at this point. What do you mean? So this is the swing diagram for a same concept that has been discussed here. So here is the relationship of tau CRRS and sigma yield point, and so there is a relationship of yield point and it is a dissolved space. The relationship. So what happens is that yielding in a material will take place when this particular denominator, cos phi cos alpha, is maximum. So that sigma L will be, sigma Y will be minimum. So that is the idea. So when phi lambda equal to 45 degree, it is minimum, so it is 0.5. So that is why this is a very important relationship. So L sigma Y equals to 2 into tau C R. So these are some of the ideas which actually discuss about plastic deformations of materials. So this is about briefly about defects, and there are other parts also when we will be discussing about the strengthening of materials. There also this concept of defects will come into picture. Then when we will be discussing about the diffusion, there also it will come. So our next topic of discussion will be diffusion, which is very important, and we'll also see how diffusions are applied in different fields, applications, etc. So in the next class, we will start with diffusion. Okay.
Okay, sir.
Yes, sir.